Here we go. What's the physics of the computation? Okay, so F equals ma is full dynamic. That's the dynamic equation of motion, right? We're not just saying F equals 0. If we were saying F equals 0, then we would only have static problems, but we have dynamic. Because we have dynamic, we have to remove kinetic energy. So then we use damping, take out the kinetic energy. Think of having a diving board that a person is going to dive off of. It's a cantilever beam. Think of modeling that as a string of balls that are bonded with parallel bonds, just like we did for the geogrid. And think of applying a load at the tip. So suddenly that board bends down, comes back up, bends down, it bounces a few times and stops. That's the idea of damping. Here's another attempt to explain the basic idea, right? There's my little simple system of a mass with a spring hanging off the ceiling. We're going to define a coordinate system. X direction is up. This is going to be concept of a force. So this is the total resultant force on that mass, right? And we take it and we finite discretize it, finite difference solution, and we play around with it, and we get this, right? We get the this is the change in velocity over change in time. And so we end up, here's we go. This is it, x dot. I'm using x dot. That's what confused me, right? This is the previous halfway back, the previous time step. This is the new time step velocity. Again, it's the force, resultant force over the mass. And in this case, there's also gravity acting times delta T. And this is just in words talking about what I said before, this idea that as waves have to propagate through the system, you basically have to just have that go during a time step from one guy to the next. Because think about it, if I have a big assembly of sand grains and I push it on the top, if I push down by one guy at the top, eventually the guy on the bottom is going to feel the effect. But in order for it to feel the effect, it has to go step, 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 step. If it wasn't that way, what I would do is form an enormous stiffness matrix that related all the stiffnesses and the springs in the whole system. And then I could invert that matrix and solve it in one step. If I did that, that would be an implicit solution, but we're doing an explicit solution. So here's my single, what happens during a time step. Here's another way of thinking about that system. We have to get the movement and interaction of bodies. So to get the movement, we use rigid body dynamics. To get the mechanical interaction, we actually properly would use contact mechanics instead of just a simple F equals, but it still ends up being a force displacement law. In general, there's two surfaces pushing against each other, and there's a complicated traction distribution in that area of contact along those surfaces. What we're going to do in the distinct element method is we're going to integrate that traction to come up with a single force and potentially a single moment, right? That's what we're going to end up doing. And this whole idea about the idea of a particle, right? In physics, a particle means one of these things with no mass. It's so small, like an electron. That's not what we mean in our world here. We're talking about discrete bodies. And so in the world of granular mechanics, people talk about particles, just like we're talking about, like stones and sand grains. So the system, particles, contacts, here's some of the things we have to keep updating, right? Position, velocity, rotational velocity, right? It's a 3D thing. It's not just translational velocity, it's rotational. Force at the contacts, right? We use the distinct element method, we move forward. Here's the contact forces. You've seen this before. We've also talked about this before, right? If you can allow detachment, if you can find new contacts, you can make these things move. That's the general thing. It's called the discrete element method. If you use an explicit dynamic solution, it's going to be the distinct element method. This is the same thing, but it's just noticing here we're updating particle position, right? Particle I, position, velocity, rotational velocity. Remember, contacts have a position and a normal vector because there's a local contact coordinate system. Remember, I shoved my knife through those two cardboard particles, and that's the position of the contact. So all this stuff is stored in PFC. That's what I mean by this. Contacts are forming. Each one has a position and a local direction. And then we also have to have these forces. So every contact also has a force and potentially a moment that has to be stored that are acting there. Now, fundamental assumptions. Here we go. In this PFC model, we have rigid bodies with finite mass and they have these shapes. Okay. They all can move anywhere they want and they have a full 6 degrees of freedom. They can translate and they can rotate. Translational degrees of freedom, XYZ, rotational, rotation about the X, Y, and Z axis, 6 degrees of freedom. They only interact at contacts, okay? And because these things are either spheres, right? They're spheres, they're a bunch of spheres glued together, or they're these sphero polyhedral. Remember those polyhedral blocks, they have rounded edges and rounded corners. Because of that, every contact is only between two particles, okay? And because we have a soft contact approach, the particles don't change their shape, but they overlap, okay? And in general, the idea is that that overlap region is relatively small compared to the particle size, okay? And then we have these things we call contact models. And that says, give me relative motion of the surface at that location, and I'm going to update the force and moment. Okay. We also have a concept of bonds. Typically, these bonds have stiffness, like the parallel bond. It actually has stiffness. It carries load. The contact bond didn't have stiffness, by the way. It's even simpler. If you bond these things, you can create clusters of particles. What do I mean by clusters? On the upper left, you're actually seeing a micrograph of a real Ottawa sand grain. So you see the length scale, 0.7 millimeters. What you're seeing here is 3 Ottawa sand grains in a little tiny triaxial cell being compressed. And here you're seeing about 20 of those in that triaxial cell being compressed. And here you're seeing in great detail one of those sand grains being compressed between 2 other sand grains, which is kind of like a Brazilian test, which is splitting it down the middle into, well, into a bunch of things, because you can actually see internally it didn't make a single fracture. It made little grains in there too. Okay. This is work by Professor Al Shibley at the bottom here at University of Tennessee, and he actually can perform these experiments, and he can get these electronic images of these systems at this scale. He uses a synchrotron as part of this process to get these things. He's done a reasonable amount of PFC modeling over the years. And so here, what you see, this is not a model. This is his magic synchrotron way of mapping the surfaces of his packed assembly. So then what he does, he says, okay, the centroid of each of these, I'm going to put a sphere. And so this could be a model of that system, right? Then what he says is, oh, wait, but I want to let each of those particles break. So each sphere gets replaced with a cluster of smaller spheres that are bonded together. Okay, they look like raspberries. And so these are the sorts of models that he has worked with. And then he's even done an additional bit of work where he represents, instead of making them clusters of spheres that can break, he takes this, and this is a rigid block. Remember, a rigid block is a polyhedra made up of a bunch of triangles. Well, you can approximate a sphere as a bunch of triangles. And these are now rigid blocks that are glued together. This would be called a bonded block model. And then he looks at the breakage of that sort of a thing and talks about it in this paper down here. This is actually showing the particle themselves are breaking, representing it at this sort of a scale. Okay. The other thing I wanted to talk about these bonds is, again, the bonds carry load, the bonds break. And therefore also, because you now have bonds, pardon me, you can have 2 particles that are not even touching and there's cement in that gap. Okay. This is again just showing equations of motion, right? Notice there's F equals ma, and there's also resultant moment is equal to the inertia tensor times the angular acceleration. And we can express the same thing in a finite difference form. And here is now the new angular velocity. It's a function of the old angular velocity, and this is the unbalanced moment about the centroid. Notice the only way that you affect rotational motion is by having unbalanced moment. And the only way that you affect translational motion is by having unbalanced force. Kind of interesting thing. And again, there's these note sets that talk about more detail how these equations come about. These equations, as shown here, are not exactly what's done in PFC. There's a slightly different algorithm that basically rewrites these equations a little bit differently, and it's called the velocity-Verlet algorithm. And you can read about that if you want. It was originally created by this guy named Verlet in '67, and that's actually what we use in PFC, and it's also described in the documentation if you really want to know at that detailed level. So again, when you just have granular systems interacting, this is what we've talked about, that linear model, normal stiffness, shear stiffness, friction coefficient. You can think of those stiffnesses as affecting the deformability. You can think of the friction coefficient as providing strength. And then this would be an example of a parallel bond, which I'm just talking about the granular material. Now we put in bonding. In this sense, we put in what we'll call a parallel bond, and it's going to now basically have to update its carrying force in the cement, and it's carrying a moment in the cement, and these are the equations it's using. This is relative normal and shear motion in the cement. This is relative rotations. It's going to have to know what the cross-sectional shape of this is so it can compute the moment of inertia, and it can compute the polar moment of inertia, because this will, for these spheres, it'll also resist twist. Okay. And then this is how we compute the outer. What we do is we think it's a beam of circular cross section, and we compute the maximum outer fiber stress that's stretching. So like if you bend a beam with moment applied, you're going to get an outer fiber stress, and that's actually going to be m times y, distance to the outside, over I. That's what you're seeing here. This is the bending moment times y, this is the distance to the outer surface. This is the moment of inertia. There's also going to be a component which is just the pulling force, the axial force. So take that axial force divided by the cross-sectional area of the cross-section, add these two together, that's the outer fiber stress. And so we look at the worst case outer fiber stress, and we say if you're bigger than the strength, which will be the tensile strength, you'll break. And we also do a same thing where we look at the outer fiber shear stress. This is the twisting moment is going to come into play. This is the shear force. It's going to come into play to cause a shear stress. And then we have a shear strength. So if either of these is strengths are if either of these quantities get bigger than their respective strengths, the system, it breaks and it turns back into a linear model. Okay. So here again, we have the same idea. Notice now, though, the way I drew this is this is like this small little surface contact business going on. But then effectively, this is a piece of glue, remember, that has a certain diameter, right? 2R bar. And so it's really as though this was a surface that was glued onto the top piece, and the green guy was glued onto the bottom piece. And it's now relative motion between these surfaces that's going to start loading up and resulting in force and moment acting on these pieces. So the parallel bond can be thought of as like an interface between the two guys. Okay. So when it's unbonded and it's broken, it's exactly the linear model. But when it's bonded, notice now it has the stiffness of the surface interaction, Kn, and that surface interaction cannot take tension. But there's also a component that represents the cement. So now it has a stiffness, Kn bar, which is stiffness per unit area. And this is the tensile strength. So it's again like a fuse. It can break, it can carry tension. So if I pull this apart, the tension is only getting carried in the cement because the surfaces are not taking tension. But when I squeeze it together, this spring is active, and this spring is active. So this material is going to have a different overall modulus when I squeeze it than when I pull it. It'll have a lower modulus in tension. This actually is really what happens in rock as well. A typical granite, like it's called lactobonic granite, has a modulus of 70 GPa when you do a UCS test. It has a modulus of about 44 GPa when you do a tension test. Very few people ever talk about this in rock mechanics. We typically just say we do a UCS test, we measure the modulus, we're done. But that's not correct. In almost all rocks, there is all sorts of initial voids and gaps and slits. Those things only carry load in compression, not in tension. So when you pull a rock in tension, there's less material resisting than when you push it in compression. So this is something that's naturally happening in this parallel bond. Okay. And then the same thing, this thing can break in shear. So it has a shear stiffness, and it also, the shear strength, here's that fuse, the shear strength is actually going to be expressed in terms of a micro cohesion and friction angle, which means that if it's a cohesion and friction angle, that strength is going to be a function of the confinement as well. Okay, so those are the parameters then. This is just talking about this. The official term for this is called double elasticity. Notice in tension, there's two sets of springs, right? This guy can't carry tension. In compression, both springs get pressed down. And here's a paper of a guy who talked about doing this. It's quite interesting. I gave this PFC course about 4 weeks ago. And the day before the course, there's this American Rock Mechanics Symposium conference that's going to happen. And I was asked to review a paper for it. And so I waited till the day before the course and I pull up this paper, and this guy did this big, huge study of parallel bonded behavior and how it compares to double elasticity and stuff. It was like, oh my God, that's quite a coincidence because I'm giving the course on Monday and it's Friday. And so I send this note to one of my colleagues and he says, oh yeah, this Arnold guy, he's going to be in your course. So that was kind of cool because I did the paper. I didn't know he was in the course. I added this slide and I took this slide out of his paper. And then I said, oh, geez, look, I stole your slide. He was actually in the course. So, and we're not going to talk necessarily about this because it's a bending business of a beam. It gets a little more complicated about how it breaks. But the basic idea, right? This outer fiber thing, it gets up to a point and it breaks. It can break in a twisting moment. You know, basically the bending moment, the twisting moment, the shear force, and the axial force, they can all force this, make this thing break. That's what we're talking about there. This is again looking at that we take that maximum outer fiber stress on the periphery of the bond. That's where this equation comes from. Force, normal force, axial force over area. This is the bending moment that's applied between the two things. This is the radius of the bond. This is the moment of inertia of a circular cross section, and a similar thing for the shear stuff going on. Okay, now let's talk about time step. Okay. This is going to be a different way to think about time step than what I talked about before. This is actually the mathematics of computing a time step because we're taking a set, we're really working with differential equation. That's what Newton told us. It's a differential equation and we're discretizing it. And so the first thing is when we discretize it using this central difference scheme, which is a type of finite difference scheme. When we're using this scheme, there is a critical time step. And we have to always make sure that our time step is smaller than that, because if we get bigger than that, this integration blows up. Okay. It turns out that this critical time step, you can do all this, you can work it out in closed form. So given the entire system of masses and springs, it's going to be a function of the entire system, all the masses in there and all the stiffnesses in there. Okay. And what's going to happen is, think of this. It's a big giant set of masses and springs. It's rattling around. Every guy is shaking around in general. And you could think of, if you looked in that system, there's going to be one guy that's shaking around the fastest, has the highest frequency. Okay. Think about we want to take snapshots of the position of every time step where everybody is. Well, we have that guy that's shaking really fast. We have to take about 3 or 4 time steps while when he shakes from one side to the other. Otherwise, we're going to miss his motion completely. And so it turns out that this is the highest frequency, smallest period of the worst case. If you figure out that value and you divide it by pi, that's what the critical time step is, which means this is the shaking around. This is delta in time of that highest frequency guy. Notice he goes up, he goes down, he goes back up. This is the critical time step. You have to sample the system at least this many places. Otherwise, it's not going to make sense and the thing's going to blow up. And the way that you compute the highest frequency in a system of masses and springs is by solving an eigenvalue problem. This is the mass matrix. This is the stiffness matrix, blah, blah, blah. So to exactly compute the critical time step for a system of masses and springs, you actually have to form the global stiffness matrix and the global mass matrix and solve the eigen and find the largest eigenvalue. This is extremely computationally expensive. Oh, and by the way, every single time step, the system changes. So you have to reformulate everything and solve it again. Clearly, no one does this because it's much too computationally intensive. So instead, we basically come up with an empirical scheme to estimate what this value of maximum frequency is, or minimum period, either one. And what we effectively do, and you can look in the manual for the details, is we work out the concept. Here's a particle, it has mass, and what we have are contacts. This particle has 3 contacts, and in the end, each contact has a normal and a shear stiffness, right? Remember, even the Hertzian thing for a given instant of time has a value of Kn and Ks. So what we have is we basically have, think of this like a cage of springs. This mass is just surrounded by these sets of springs, and he's vibrating back and forth. So what we can do, knowing this information, we can compute, I'll call it an equivalent translational stiffness and an equivalent rotational stiffness. This is supposed to be a rotational spring, like a watch spring. We can compute those things for every single particle. Okay, and what we find is that particle's critical time step is going to be this, the square root of mass over translational stiffness and moment of inertia over rotational stiffness. Think of it this way. Think of if you had a fishing rod, which is a big cantilever beam, because you're going to grab it in your hand and it's going to be vertical to the floor. You're going to take that fishing rod and you're going to shake it and it's going to start to vibrate. Okay. The stiffer that rod is, the faster it's going to vibrate. And so if it's vibrating faster and you want to track that motion, you have to take smaller time steps. Okay. And so that's why the stiffer it gets, this is the denominator. The stiffer it gets, the smaller the time step is. And similarly to the mass, if you added mass to that thing, it would shake slower. And so thus you could take bigger time steps. Okay. To illustrate this idea, I wish I could say I did this. Someone actually constructed a physical model of tennis balls connected by springs. And of course, these are physicists. They get to do all these fun, crazy things. And look at what it does. They built themselves a physical manifestation of a PFC model, right? This is, remember that thing when we had them glued together and we smashed it and they were going tension, compression, tension, compression? That's what this system is doing. Okay, so this is the PFC model. It is a bunch of springs joining a bunch of masses. So notice that this critical time step is based upon the mass and the stiffness in the system, because what we do is this gives you the critical time step for one particle. Okay, and what you do is you figure out the critical time step for all particles and you take the smallest. Okay, and so it's based on mass and stiffness in the system, and it may change, right? When you start squeezing the system, you start to get new contacts, you get new springs. Um, and so that's potentially going to make it stiffer, that's going to make it vibrate faster, that's going to make the time step have to get smaller. So it's happening, it's changing, you don't control it. Okay, there's a command: model mechanical time step auto. Okay, um and that's all I want to say about it in this point here. Okay, so it's basically, you just have faith that we did this right and it's working in the background all the time. Okay, um not going to talk about mass scaling. um if you want, for certain types of problems where you really know what you're doing, you might want to actually fix the time step at a certain value. But of course, you have to fix the time step smaller than the critical. We do not let you make the code go unstable. We don't let you do that. So we still always know the critical time step. And if you want, you can make it smaller. Now, damping, right? Remove kinetic energy. Okay, there's different types of damping. There's basically this thing called local damping that we're going to talk about. And for almost all cases of the work you guys are going to be doing, you're going to use local damping. There's also other types of damping, like when two guys come together, there's a dash pot. That's going to remove energy. That's a type of damping. It's even built into these contact models. Um, and there's also a hysteretic damping, means if you push two surfaces together and you pull them back, there might have been a hysteretic response where you lost energy. So there's those sorts of dampings, but for most cases, we're going to use local damping. And what it's going to do is it's going to think of those vibrating tennis balls again. Imagine that you went, so you just zoom in on one tennis ball, okay? And it's in the current problem, based on how it got loaded, it's vibrating. And at any given instant, it's just vibrating back and forth in a certain direction, right? What I'm going to do is I'm going to say, I'm going to come up with a magical damping force, which is an additional force acting on the system that doesn't really exist, but it's going to be applied. And what it's going to do is it's going to act against the direction of unbalanced force that mass feels. So we sum up the forces on a mass, and that's the direction it wants to start moving. And so we say, oh, you want to start moving this way? We're going to push against you. So like if you were a person, if it was Mustafa was that mass, and Mustafa had this acceleration in a certain direction, and he's facing that direction, I'm going to stick my finger on his forehead and take energy out of him and slow him down. This is done individually, separately for every single mass. Therefore, it's done locally, and we call it local damping. And so what you end up specifying is a single constant called the damping factor that gets applied separately to every ball. Every ball has its own damping factor. So what it does is it looks at the unbalanced force on that guy, and it says damping factor times unbalanced force. That's the force in my finger that I'm going to use to push back. So the damping factor will go between 0 and about 0.7. Just think about this. There's an unbalanced force currently. Well, if I apply a force that's 10 times bigger to push against the forehead, I'm going to massively affect the response of the whole system. I don't want my damping to mess up the general response. I just want it to slow down the shaking. So that's why the damping typically goes between 0 and 0.7. Okay. And this is just the equations here. Notice this is the equation of motion: change in velocity, change in time, math. This is the result, sum of all the contact forces. There's the magic. It's that force. It's my finger pushing against Mustafa's forehead. That's the damping force. How do we compute it? Damping factor, and this is the unbalanced force. Okay. And you control this with a command. You tell it every ball has an attribute that's called damping factor. So you give the command ball attribute damp 0.7. Okay. We'll see examples of that. Here's the idea. Some of the contact models have built-in dash pots. Okay, we call this viscous damping. Okay. Sometimes you might want to do that. Typically, we don't want to do that. This type of damping is velocity dependent. Depends on how fast you're shaking. If there's a dash pot, if you're shaking really fast, you're going to get damped more. But But sometimes you want to do viscous damping, and I don't even talk about hysteretic damping. I think I don't mention that. Oh, hysteretic. There you go. This local damping is not physical. It's a magical thing to very quickly stop the vibration of the system, because every single guy gets specially tailored force to make that guy stop shaking. But if what you want to do, so for example, if you take a box of grains of sand, you model them as particles, you let them settle under gravity into a box, and now you slowly start squeezing it, you are exciting the system, and that whole system is going to start shaking like those tennis balls and springs. And this is the type of thing that this damping is going to basically keep at a negligible level, so that you don't start getting that whole thing shaking like crazy. So therefore, you can do this. If you load that thing slow enough, it basically is going to behave in a quasi-static fashion. Okay. Now, the next thing, how do we know when our models are at static equilibrium? Okay. So think of, again, this big collection. Think of oh God, yeah. Think of the picture that we just saw of the tennis balls and the springs. And like, that real system, right? After, 10 or 15 seconds, it's going to stop shaking, right? Because there's some type of damping mechanism going on when you're stretching those springs, and unstretching them, you're losing some energy. So one thing you could do is look at the springs, and look at the tennis balls, and look at the velocity of each one. And when the velocity of each one is 0, you're done. All right. That's the definition of static equilibrium. Nobody's moving anymore. All the forces are in balance. Well, you could do that with your PFC model as well, except, oh, sorry, you can't, because we don't use real arithmetic, because we're on a computer. We use finite precision arithmetic. And so when we don't store all of the continuum value of real numbers, we just have discrete real numbers. We talk about floating point accuracy. And so on a typical modern computer now, you got 13 digits of precision, which means if you take a sum of forces, you come up with the resulting force, which what we'll call the unbalanced force. And even if it really is, it's never going to, what I'm saying, it's never going to equal 0. It's going to equal some number that's on the order of something e to the negative 13 or e to the negative 14. Okay. So you say, okay, well, that's fine. So why don't I just run the system until all the velocities are e to the negative 13? And you could do that. And it's going to take a huge number of cycles to reach that. You're going to find that by the time the velocities are maybe 1 e to the minus 6, the force chains are no longer changing, which means nothing really is happening of interest. And you can probably say I'm good enough, and I can then just go on with life, and I can then do the next step. Right. So like, I've let them settle into gravity. They're good enough. That also would be a pain, because you would like to have some automatic way of doing this. And so we have this concept of a solve command. So we give a command, model solve, and then we give it a certain there's different criteria to determine, are you close enough to static equilibrium? One of them is this average unbalanced force ratio. And so what you do is, don't look at the equations. What you do is, here's a particle, you sum up all the forces. That resultant force in PFC, we typically use the word unbalanced force, okay? Because if it's unbalanced, it means it's going to make it start accelerating. So you take the resultant force here, and now you have to you can't compare it to 0, we already talked about, but you can compare the ratio of that force over, just think of the total sum of all these forces. If you just take the magnitudes of all these guys, that gives you some kind of metric of what's happening to this guy. So you sum up the magnitudes of all these guys, you put that in the denominator, and then you take the unbalanced force and you divide it. And if that ratio, you want that ratio, eventually it should approach 0. And it turns out that when you use that at about 1 e to the minus 5, you pretty much have static equilibrium. When we start running our stuff on Tuesday, we're going to look at this, and we're going to convince ourselves that, oh, look, yeah, really nothing is happening anymore once we reach to that ratio. So what you do to make an assembly of sand grains that are in a box, you generate a cloud of them, you turn on gravity, you have your box, you let it run, they fall to the bottom. They shake around for a while. Remember, we have damping on there now. They shake around for a while, and you just give this command, and it's going to keep running until they're in equilibrium. So that's what you're going to do. Okay. So that's this idea of convergence. We use the model solve command. Okay.